Let me introduce Bastiane a little bit. And she is sharing from San Francisco, and she has an extensive experience in automation and manufacturing industry. She is now the product manager of Osaro. The talk will not only share the AI-enabled robots are used in the warehouse, and will also share the technology Osaro developed to address the challenging industrial robots. So let's give Bastiane a warm applause and welcome her talk.
Thank you for your introduction. Can everyone hear me well?
Yeah.
Cool. Good morning, everyone. My name is Bastiane. It's my pleasure to be here and talk about next generation artificial intelligence enabled robotics. I'm sorry I cannot be there physically, but I'll try to make the next 1 hour as interesting as possible. So I thought I would give you a brief introduction about myself before I start my presentation, so you have an idea about who I am and what I'm working on. So here's the introduction. So I'm currently a product manager at Osaro. I'll give you more introduction about this company. Essentially, we are a San Francisco-based startup building machine learning software for robotic vision and control. I was born and grew up in Taiwan, and I studied information management at National Taiwan University. After graduation, I joined a few companies. I did product marketing and business development at E2B, a British aerospace and defense company. Then I worked for Advantech, was responsible for growing the business of intelligent video software and IoT platform. So we did things like facial recognition, people counting, gender identification, etc. And before I went to business school, Harvard Business School for my MBA, I worked for Taiwan Startup Stadium as an IoT manager to help foster the startup ecosystem. So I'm especially interested in startup, especially with the new technology driven by startups. I'm extremely passionate about artificial intelligence and robotics. So I wrote a few articles and a business school case about AI and robotics for Harvard's Managing the Future of Work initiative. I also have a couple of articles published on robotics business review. So feel free to check out my Medium if you're interested in learning more about the articles I wrote. So now going back to our topic today, next generation AI-enabled robotics. Over the past year, many people have asked me what's actually going on in artificial intelligence and robotics. They wonder how are AI-enabled robots different from traditional ones, and what are their capabilities and limitations. Interestingly, if you ask people how they think about robots evolving over time, this is usually what you get. People often picture robots changing their appearance and looking more and more like human, while in reality, the biggest change that we've seen in robot evolution is actually something you cannot see from the outside. It's the intelligence and autonomy brought by machine learning. And this is what I'm going to talk about today, what we call Robot 2.0, or next generation AI-enabled robotics. I'll first start with a brief introduction about Osaro to give you a sense of who we are and what we are working on. And then I'll talk about AI-enabled robotics. What is it? How is it important? Why is it important now? And why is it particularly relevant now? I will also talk about a few machine learning research areas that we've been looking into, including things like deep learning, reinforcement learning, imitation learning, and meta learning. I also touched on some of the challenges and opportunities that we've seen, our approaches in addressing these issues, and finally, I'll end this presentation with our thoughts on the future. So, at Osaro, our mission is to build machine learning software that enables robots to learn and adapt to changes in the environment. Our first product is an e-commerce fulfillment software. It's a robotic piece-picking software for e-commerce fulfillment centers. We're also working on projects with customers in food assembly and advanced manufacturing industry. So here are our co-founders, Derek Kumar, our CEO, and NK, our CTO. Essentially, what we're doing is to build brains for robots. The company is based in San Francisco and was founded in 2015. and we currently have about 13 employees, mostly deep reinforcement learning and motion planning engineers. And what we focus on as edge deployed end-to-end robotic perception and control software. So we don't really sell robot arm. We don't sell any hardware. We only focus on software. So we have a software as a license model, and we distribute our software through system integrators. Particularly in warehouse automation industries, there are top 20 material handling equipment system integrators accounting for over 85% of market share. And we're currently working with 45% of them and most of the major robotics companies. So the biggest difference that machine learning brings to robotics is to enable a move away from having to hard program a robot to true autonomy. You don't really see a difference if the robot only does one thing. But if the robot needs to, for example, respond to people, react to changes in the environment, handle a wide variety of different tasks or items, then it needs a certain level of autonomy. We can borrow a definition for self-driving car to explain different levels of autonomy for robotics. So as you can see, there are 6 different levels. From level 0, which is essentially no automation, people operate a machine and robots are not involved, all the way up to level 5, which is full autonomy across all situations. Right now, most of the robots you can see in the field are actually in level 1, what we call open-looped or non-feedback control, which means the robot doesn't really take any sensory feedback from the environment. You can also call it single automated operation. That means that the robot is automated, is programmed to perform a single task repeatedly with high precision and high speed. But even if there's a small change in the process, for example, if I move this electronic parts to the left by 10 centimeters, the robot cannot respond. Someone needs to step in and reprogram or recalibrate the robot. There's few robots in the field actually take and act based on sensory feedback. That's called level 2, partial automation. For example, you can attach a machine vision camera to a robot arm. The robot can now recognize different objects and the environment surrounding it. But traditional computer vision requires each object to be pre-registered beforehand, and you still need to program the robot to be able to respond to each of the different objects. It's still not full autonomy. The robots cannot respond to surprises or new objects. We've begun to spot some pilot projects with AI-enabled robots for conditional or high autonomy, level 3 or level 4. Warehouse piece picking is a very good example. Traditionally, in automated warehouse, you have Kiva, mobile robots like Kiva moving boxes around, but you still need a human to literally pick and place different objects into the boxes. That's because usually in typical warehouse, you have millions of products. So you can't really pre-register millions of products and program the robot to be able to respond to each one of the millions of products. But now, with deep reinforcement learning, it's possible to teach the robot to handle a variety of different items with its minimal supervision from human. There might be some new objects the robot never encountered before and therefore need some help or demonstration from people. But gradually, as the robot collects more information and learn from trial and error, the algorithm will get closer and closer to full autonomy. So what exactly is deep reinforcement learning? It's essentially a merger of 2 techniques, deep learning and reinforcement learning. I won't get into too much detail here, but essentially deep learning is image recognition technique primarily used for image classification using deep neural nets like this trained with labeled images. So as you can see, each layer will transform the input into a slightly more abstract and composite representation, and eventually the machine learns to recognize different objects. When it comes to control domain, label images are not required. For example, you can think about when we are trying to learn how to walk, we aren't really given a vast number of label images with joint angles. Instead, we just try to walk, and we get a generally weaker signal of falling over, so we know that we need to adjust the way we walk, and gradually we learn how to walk properly. Similarly, in reinforced learning, you have an agent. In our case, it's usually a robot. It chooses an action based on its current policy. A policy is just a way of acting. It then gets a reward from the environment for executing the action, learns from the reward, moves on to the next stage, and chooses another action. It repeats this process with the goal of maximizing the long-term return, and eventually it learns the policy that we're trying to reinforce for it. So when you combine these two, you have deep learning allowing a robot to recognize different objects around it or in front of it, and then you have reinforcement learning to allow robots to learn different policy to handle objects. So now the robot can learn to recognize the items in the warehouses and learn to handle the objects in front of it. So why is it so important? Because essentially enables a move away from having to harbor with robots, because now people don't necessarily need to be in the loop. So you can save time and engineering resources. Also, in most of the factories, you see a lot of surrounding systems around the robots, like the shaker table, conveyor belt, or feeders. This is because right now, the robots don't take any sensory feedback from the environment. So essentially, robots are blind, they don't know what's going on around them. So you have to have feeders or conveyor belts to make sure the parts are delivered to the robot at the same place and same angle every time. But what if we can make robots more flexible and more adaptable? They can also become less dependent on the surrounding systems, which is usually more than 4 or 5 times of the cost of a robot. So we can save significantly on system integration. And they also help address questions that are traditionally difficult to describe to computers. For example, if I want to teach a robot to recognize cats, I may come up with general description like, a cat has 4 legs and 2 pointy ears, but how is that different from a dog? So for this kind of problems, it might be easier to just feed the machine with a lot of different data and let the machine learn by itself. It also helps the machine to learn to handle variabilities and react to changes, because now the robot becomes more dexterous and more flexible. And finally, it allows the robot to learn at scale. Imagine you have a robot learns to plug 2 items together, for example, overnight through trial and error. It can share its learning to a fleet of connected robots by uploading its model to a cloud, so the rest of the robots don't need to repeat the learning process. So it's much more efficient, it's much more scalable, and it also ensures consistent quality. So this technology will eventually change the comparative landscape across different industries. I just want to give you more idea about why this is so necessary in the real world. This is just a subset of items we tend to pick in typical warehouses. As you can see, it simply has too much variabilities. A typical warehouse has millions of products. And it's not just about the type of products, it's also about the packages. For example, clear packages, translucent packages, and reflective surfaces often make it really difficult for a traditional 3D structuralized sensor to recognize, not to mention deformable or flexible items. And here you can see all kinds of different items, like for example, the clear box on the top right. You have to train the robot to be able to pick the entire box, not just what's inside. And for the gloves, you have to target the label instead of glove. And you need to aim for the body and avoid a pump for the lotion bottle. So it's just a lot of nuances and rules that you cannot really program explicitly. You have to let the robot learn by itself. And so why is this particularly relevant now? In 2017, we saw that robot sales increased by 30%. And hit 387,000 units. It's a record growth of industrial robots. As the robot production increased, the costs have gone down significantly. The average robot price has fallen by half over the past 30 years. In real terms, even more if you compare that to increasing labor cost. As the demand from emerging economies continue to soar, we expect the robot price to keep falling. But on the other hand, we have this global problem of shrinking labor force driving up needs for automation. Especially in countries like Japan, for example, Japan's population is expected to shrink by 24% by 2050, and its working age population is expected to shrink at an even faster speed than its overall population. But if you look at the data, the average age of farmers in Japan is already 70 years old, and 1/3 of its construction workers are over 55 years old. So this is really an urgent problem for many countries. And for certain industries like e-commerce fulfillment, this kind of labor shortage really drives up the salary. And this is already an industry where the jobs are really difficult to fill and talents are really difficult to retain because the tasks are highly repetitive. Just to give you a sense of how repetitive the tasks are, this is what a typical automated warehouse looks like. And the system in the background is called ASRS, Automatic Storage and Retrieval System. So this ASRS will retrieve, conveys, and delivers different products in a single SKU donut tote and deliver it all the way to the picker's workstation. And the picker will pick and place different objects into the bin in front of him or her. So for example, if you order 3 bottles of shampoo on Amazon, this picker will literally pick 3 bottles of shampoos and put those 3 items into the bin in front of him. So as you can see, this is a highly repetitive task. This probably explains why the turnover rate is so high, generally around 14%. And US companies lose about $11 billion every year just due to employee turnover. The direct cost to replace an employee can be as high as 60% of the employee's annual salary. So this is why a number of customers, system integrators approached us and want us to develop an automated solution for this. So here I just want to show you a video of an early prototype that we create. So as you can see, the system is pretty simple. The camera takes the image of the bin and the robot arm goes down and pick one object, scan the object and barcode at different angles and put the item on the conveyor belt and just repeat this process. So as you can see, this is a fully automated solution and alleviates the turnover rate problem that we just talked about. So what we're trying to do is to automate this stationary picking solution, which is right now the most labor-intensive task in the automated warehouse. And this is done by integrating our software with an automated storage and retrieval system. And this is a level 4 autonomous system with no human in the loop. So this is what a system looks like. What we're trying to provide is a scalable software-based picking solution. So as you can see from this diagram, multiple cameras are used to either attach the robot arm or fix it in the environment to collect more data for training. And the data and models are stored in the cloud. And the cloud is connected with a local PC for local execution, like planning or simulation. And this local PC will also be interfacing with PLC, Programmable Logic Controller, and Robot Controller for real-time control of robot mechanism and joint angles. And this whole system will then integrate it with warehouse management software for a high-level coordination and planning. So what we do is essentially first collect data through simulation or actual robot rollouts, then train a model based on the collected data, test the accuracy and generalization of the model, repeat this process until we have a highly accurate model that we can deliver to our customers. So here I just want to quickly go through a few machine learning research areas that we've been looking into in order to implement our machine learning solution. We already touched on deep learning, and I think most people here probably already heard about deep learning. So essentially it's very good at learning rich representation using deep neural network. It's really powerful in supervised learning problems, and we've seen a lot of success across different range of problems without domain understanding for feature introspection. However, the biggest problem with deep learning is that it requires a large amount of labeled data, and it's often very time-consuming and expensive to collect that much labeled data. So that's why we only see most success in supervised learning problems. Even though right now, for example, you can see some occasional success in unsupervised learning problems, like with games, but mostly the success is still confined in supervised learning problems. And it's hard to interpret because deep neural network acts like a black box, so you don't really know what's going on inside of the algorithm. It also requires the high-end infrastructure, so at least you need a GPU, so it's more computational expensive than traditional solutions. I want to also talk about motion planning, because this is not something people often associate with machine learning. So motion planning is basically a technique to determine a path between two given points for robotics. So it sounds very straightforward, but it becomes a really complicated problem if you consider the kinematic and dynamic limits of the robot and environment. It's really important because when you operate a robot, you want to make sure the robot is running smoothly and achieve the desired task with the highest speed and accuracy possible. You also want to make sure the robot avoid any obstacles in the environment, and you want to make sure that the robot doesn't hurt any people around it. So safe and collision-free robot path planning is pretty important. The different ways to implement motion planning, for example, sampling-based motion planning means that you search for collision-free paths by through sampling points. And gradient or optimization-based motion planning means that you define a loss function and you solve the motion planning problem as an optimization problem with the collision as penalize the collision with the loss. So optimization for motion planning is really important, but optimization can be also very time-consuming because it's an NP-hard problem. For our particular application, robotic manipulation, pick time is really important. How many objects you can pick per hour is essentially affects on your return on investment. So we really need to be very mindful about the trade-off between pick time and optimization. It also suffers from the curse of dimensionality when you're trying to increase the degree of freedom. So that is to make the robot more flexible. And it's also sensitive to environment changes. So if there's any change in the environment, you will have to do the motion planning all over again. And we know that oftentimes collecting data and testing with real robot is really expensive and time-consuming. So that's why data augmentation, synthetic data, or simulation can be really helpful. Because it's usually easier to label, faster, more scalable, less expensive, and safer because you're not actually operating a robot or operating a car to collect more data for deep reinforcement learning algorithms. It's also more data efficient, but it requires a more accurate model of the problem. And oftentimes you cannot simply transfer the model from simulation to reality because there's a skill gap. So you want to be able to use very realistic simulated data, but that's also challenging because right now it's still very difficult to simulate physics like gravity, friction, or context. There are some research teams like in OpenAI or in Berkeley, they're working on domain randomization. Basically, the idea is that if the deep neural net sees enough simulated variation, the reality may seem like another simulator, but it also makes the learning task more challenging than it has to be because right now the model needs to learn new tasks and model arbitrary changes. So we also touched on reinforcement learning. We know that the goal of reinforcement learning is to solve sequential decision-making problems like picking an item or walking, for example. It's really appealing because it allows machines to autonomously learn by interacting with the environment with minimal supervision from human. So previously, what DeepMind did with AlphaGo Zero is essentially applying reinforcement learning. and allow the algorithm to self-play by itself with with almost zero data from human. But the issue with reinforcement learning is similar to what's with deep learning. It requires a very large sample complexity, and we know that's very expensive and often not feasible to collect such amount of data in real-world domains. And that's why the current success is most limited to simulated environments like games. So when it comes to robotics, it's really difficult to just rely on simulated data. And it also has a stability issue when it's used simultaneously with representation learning because the two areas don't necessarily converge. So one approach, imitation learning, as a potential approach to solve some of the issues that we just talked about for reinforcement learning. Here I just want to show you an early demonstration we did back in 2016 about imitation learning. So this was recorded back in 2016. Our system has changed a lot since then, but to still give you an idea about imitation learning. So essentially, imitation learning is targeted at solving and learning control policy with expert demonstration as training data. And it addresses the sample inefficiency and computational feasibility issue that we just talked about by giving an agent prior information about the world through mimicking human behavior. So if you think about us human, when we are trying to learn different things, like for example, trying to learn how to ride a bike, oftentimes we have some demonstration, someone tries to teach us. We don't normally learn from scratch. So imitation is a similar concept by basically learning from an expert demonstration. So it's particularly useful when the reward function is sparse or difficult to specify or optimize directly. But it has a compounding error problem when the agent drifts away from expert's demonstration, and also it's also expensive and difficult to collect the expert demonstration. But the biggest issue with imitation learning is that it only copies the behavior. It doesn't necessarily learn the objectives behind the problem necessarily. And that's why the trend policy is only as good as demonstration. So as you can see from the video, sometimes the demonstration is not the most optimized or most efficient way of performing a task. So we want to be able to adjust or optimize it instead of just learning the behavior. So similarly, meta-learning is not a way to reduce the amount of training data required and speed up the learning process. The idea is to design models that can learn new skills or adapt to new environment rapidly with just a few training samples. Early approach is just to automatically fine-tune hyperparameters or learning algorithms and now it's more generally trying to teach machine to learn how to learn. So in meta-learning, you have meta-learner, what we call an agent, and learner, which is a model. And the agent will train the model with a training data set containing a vast number of different tasks. And in this stage, the model will acquire previous knowledge and learn a common feature representation across different tasks. So when there's a new task to learn, the model will be fine-tuned using the training data brought by the new tasks. So that's why the model can be quickly adapted to new unseen tasks. So it's much more scalable and addresses sampling efficiency problem that we just talked about. But the algorithm can be much more complex, and the training can take a long time, sometimes it's several months, and it requires a careful design of training procedure. And finally, transfer learning is defined as using experiences and knowledge from solving one task and apply it to solve another different but related problem. So for example, Think to Real is one area of applying transfer learning. So you can train a model in simulation and trying to use the same model to solve real-world problems. It's really useful because many tasks share a similar or underlying structural representation, but it's still an ongoing research area, and it has a negative transfer problem when the source and target domain do not overlap much, and the target domain may learn from unrelated examples from the source domain. It's also hard to measure transferability. There are also other issues with this, not just machine learning related, but also very challenging. So we already talked about real-world sensors are often very noisy and fail all the time. And for example, traditional 3D structuralized sensor cannot recognize translucent and reflective surfaces. So what we do at Osaro is train deep neural architectures, not just to learn representations on the object level, but also on the pixel level. And we also do things like semantic segmentation and background understanding, so that we increase our understanding of the image, so we can recognize different objects with just commodity cameras. And integration and connectivity is definitely another issue. Oftentimes in factories or warehouses, you don't really have stable internet. So you need to make sure that your software can run offline and can cache the data and upload the data whenever there's internet. And besides bandwidth and connectivity constraints, you also need to make sure your software is integrated with the surrounding systems and the commodity power. And that's a challenging problem because this industry is extremely fragmented. You have robot makers like KUKA, ABB, or FANUC. They all have their own individual proprietary languages and control interface. And all the system integrators, they will have their own preference in terms of robot and factory and sensors. So you need to make sure that your software support all of these major platforms and provide as much flexibility as possible. And we know that deep learning and reinforcement learning requires more data, so they often improve over time as you get more data. But in reality, most customers want the model to just work perfectly. If there's any additional training required for new type of objects, it needs to be very quick and continuous. And everything needs to be measurable and interpretable. And if there's any change in the environment in terms of lighting or environment setup, the model needs to be robust to all these changes. So for the same reason, metrics are also really important. You want to be able to provide customers with the information like peak time, accuracy, error or failure if there's any, so that the customer can know like how to improve the system. And you also want to provide system-wide performance like operation time, uptime, or fixed to date stack time distribution to show that your system improves over time and is robust to any changes in the environment. For the same reason, user interface also matters. It has to be simple, intuitive, but still covers all the functionality and flexibility required by customers. So you want to be able to provide customers with the ability to set up environment, choose different planning modes and different models, and being able to quickly add the behavioral tree and collect data, store data, as well as access evaluation metrics and custom analytics. So we already know that deep learning requires a lot of training data, and its performance outperform traditional algorithm when there's a large amount of data. But it's also difficult and expensive to collect data in real world. So definitely think about what we just talked about, things like simulation, data augmentation, synthetic data, as well as transfer learning and meta learning, any way to help you address this data-hungry nature of deep learning. And especially think more about your data strategy when you are in the industry where industry giants own most of the data. So we've talked about a lot of progress made in the area of AI-enabled robotics. But to be honest, we're still very far away from the ultimate dream of having robots to fold our laundry and fix our cars. So we have to be very pragmatic and start with more scalable use cases. So we know that there are research teams working on meta learning and transfer learning. But until we can really address the issue of generality, we still need to start with more structured tasks with with less task complexity or fewer. The warehouse piece picking is a very good example, as a low-hanging fruit is as a first starting point for AI-enabled robotics. But sometimes scalable use cases are not that easy to identify. For example, in manufacturing, assembly tasks vary from factory to factory. So it's difficult for you to come up with a standard solution that can be used at multiple factories. So our key takeaway in designing machine learning solutions at scale in real world is that it's really interdisciplinary. It's not just about machine learning, but you have to design the solution for tight integration and support commodity hardware and sensors around the system. It has to be verifiable and provide analytics, and you need to be able to manage your data pipeline and be extremely pragmatic in terms of the tool to choose for the job. So I just want to show you as a summary the solution that we came up with. So this is our first product. It's called Osaro. It's essentially what we talk about as a robotic vision and control software. It's used mostly in e-commerce fulfillment center, and as you can see, we can deal with transparent objects with fast check time and high accuracy. So the model generalizes across different items, and then software supports different robot arm, hardware platform, and different manufacturers. As you can see, we use structure cups and 2 fingers here. And it can pick not just from a single schedule, but also a jumbled data. So sometimes it can pick from the size if it has to. So we also support 6 degrees of freedom. So the robot can also learn to recognize deformable items. And picking food is actually an interesting case where I will talk more about it. But here, as you can see, every chicken nugget has different weight and shape. So you really cannot program the robot to do that. You have to use deep learning to recognize each of the objects. And we also do intelligent placement. So I just want to tell you more deep learning based vision models that we used. So here, the image you can see in the middle is essentially applied with our proprietary mask algorithm. So you can see bounding boxes of each of the objects with relevance, or what we call region of interest, ROI. And we use semantic segmentation for the coloring. So the blue parts here you can see on the brushes, the handle part. That means the blue parts mean the pickable areas. So the machine learns that for this kind of brushes, if you use suction cup, it has to pick from the handle, it cannot pick from the head. And here, this video here shows that we do semantic understanding and scene understanding. So even though you change the orientation and location of the bin, we can still recognize different objects. So we can still localize dynamically key signal items. That's why the software can be robust to changes in the environment. And here an eye drop is actually pretty difficult to pick, but overnight somehow the robot learns to pick it up this way. So sometimes the robot come up with ways to do things that were never expected, and this is why the reinforcement learning is so appealing. Right, so the reason that we talk so much and spend so much time and resources looking into this area is because we believe there's a huge potential with AI-enabled robotics. This is from McKinsey research, and basically McKinsey did a report and they identified industries with the most predictable physical works. And the top three are accommodation and food, manufacturing, transportation, and warehousing. This means that these industries can be more likely to be automated by AI-enabled robotics in the future. And that's why warehouse automation, or ASRS, is really just a small market. It's really just a start. As the technology improves with its accuracy, with its adaptability and generality, we can apply the solution to a lot more different industries, not just in warehouse, but also in food, automotive, and electronics. So I want to end my presentation with two more examples in the adjacent markets. We already talked a lot about warehouse industry. And here's an example, a project that we did with one of the robotics companies for an automotive industry customer. So here we use tactile perception, so no vision, no camera is involved in this project. We use tactile perception with imitation learning to train the robot to be able to fit packs and holes together. So it's a robust solution. It works with off-the-shelf sensors. So as you can see, the robot learns to basically fit the plates together with tactile sensor. And it's robust to changes in the environment. So even though we change the parts geometry, it still learns to recognize the surrounding environment and fit the packs and holes together. Cool. So one last example I want to talk about before we end the presentation is essentially food assembly and preparation industry. This is a very, it's a big industry. Just the bento box assembly industry in Japan alone is a 70 billion industry, and they don't have enough people to assemble bento box because of aging population. So as you can see, the system is pretty much the same as what we already talked about. And I can show you a project we did with Denso, a Japanese robotic company. So we demonstrated this bento box assembly system at FUMA Machine Exhibition in Tokyo. Denso has their own AI team, and they're trying to figure out how to do bento box assembly demonstration. But their AI team cannot figure out a way to recognize the chicken nugget because the camera will recognize the pile of chicken nugget as just one object. So we got involved and finished this integration within 10 days. So what we essentially did here is to use fully convolutional neural network to learn representation at pixel level. So that's why we can recognize different chicken nugget items instead of just learning it as one object. So you can see that we have graph points for each of the objects. And we use compliant paper to pick the object so we don't really damage the food items. And it still works even though you change the lighting condition and use a commodity camera. And for food industry, it's really important to ensure the sanity of the system. So that's why the robot arm is covered. So with that, this is basically everything I want to present to you today. So here's my contact information in case you have any further question and you want to talk more about AI-enabled robotics. And here I also included my Medium if you are interested in reading more about the article. So with that, thank you so much for your time and attention today, and I'll be happy to take questions.
Bastian, you can look at the question list on Slido. Do you have the link?
Yeah, I'm just looking at the list right now.
Okay. The first question is in Chinese, so I will repeat it. 这题是在讲说，之前因为 Bastian 的经验非常丰富，然后也曾经在台湾的大厂还有欧美大厂待过，然后蛮好奇，像刚刚分享这么多，就是工业自动化还有机器人领域的发展，就是你是怎么就依照之前在欧美跟亚洲的经验，是怎么去看现在这两个产业目前这两个区域的产业在市场需求还有发展资源上是否是相当的？就是发展，就是你有什么感想或是经验可以跟大家分享
？Should I just 我要用中文还是英文啊？
都可以。
Okay. I think it's mostly because this is a very broad question. But I definitely see a huge difference in terms of companies in Asia and companies in the United States or Europe, the way they see innovation in artificial intelligence and robotics is definitely different. First of all, from a market demand point of view, we definitely see a lot more market demand from Asia. This is because most of the factories and most of the warehouses are in Asia. So for sure, I think there's no doubt that we have strong demand from Asia. However, right now in Asia, or in South Asia, or in countries that with lower labor cost, we don't really have that much incentive to adopt automation and solution right away. So for countries like Japan or Germany, because they're facing serious aging population issue and their labor cost is really high, so they have more incentive in adopting solutions like ours. So when we talk to customers in Europe or in Japan, they're more likely to start experimenting with our solution. Versus if we talk to companies in Thailand, for example, or in China, they don't have such urgent need to adopt our automation solution. So I think that's one of the key difference. And secondly, I think U.S. companies tend to spend more time and resources on research and development. And I think this is still true. Like, I'll give you some example. Like at Osaro, every Wednesday, we have a weekly paper reading section, which essentially we read research papers from different universities like Stanford, Open, or not just university, but also OpenAI and Google X, for example. We read the latest research paper and then think about how we can actually apply this research on our products. And I don't see this happening with a lot of Asian companies in general. We do see, I do sometimes see Japanese and Korean companies working with universities, Chinese companies too, but inside of the company, I don't see a lot of people actually reading the latest academic research and think about how to apply it on the robots. So I think Asian companies in general are more pragmatic. They think more about how they can apply the current technology and just introduce the technology to the market. But US companies think more about how to be much more innovative. And this is there are many reasons to that. One of the reasons is that the capital market is very different. Like the VCs in United States and VCs in China, because we are invested by venture capitalists in different countries. So we see the difference where venture capital firms in United States tend to be more patient than venture capitalists in Asia in general. So they're willing to wait for you to come up with more innovative solutions versus pushing you to have more revenue. So there's no right or wrong or good or bad. It's more like US companies and Asian companies, they tend to have different approach in terms of innovation and go-to-market strategy.
Okay, then maybe we can look at the first question on Slido. How do you accumulate the domain know-how in so many fields, including industrial IoT, automation, robot, or in your point of view, they actually have many in common?
Mm-hmm. Yeah, I'm actually pretty focused on basically IoT or AI solution. The intersection of IoT or AI with physical world. So I don't really pay a lot of attention to AI solution in virtual world, like for example, gaming or videos or just pure image recognition or advertisement. That's just because my personal interest and also my background, because I spent many years working in hardware companies like ETV and Advantech, so I feel like I have much more experiences and connection in those industries. So when I'm trying to choose my job after business school, I pick areas that I'm more familiar with. So I want to do artificial intelligence, but I know it's a very broad area, so I need to be very focused and find the area I can really specialize in. So I only pick artificial intelligence areas that's intersected with physical world. So that's the only two areas that's like that. One is robotics, and the other one is self-driving car. So I'm actually pretty focused on very specific areas, because I think it's right now, many people are very interested in IoT or AI, and they're just like buzzwords. And if you're trying to learn more about these two areas, they're just too broad. You definitely need to segment it and then try to pick the areas you are most interested in. Otherwise, there's just too much information to digest. So my approach is to lay out the landscape with the industry and pick the industries I'm most interested in, or I think I'm more experienced in, or I have more advantage in, and then just spend more time in those areas. When I think business school definitely help a little bit, because school help you broaden your horizon. When you are working, most of the time you are very much focusing on one industry, one application, or your specific function. But in school, you're allowed to explore a wide range of different areas. So I really like that part of school. You have 2 years where you can really explore anything that interests you. So I use that time to actually list down all the areas I'm interested in list down all the companies in these areas and talk to them one by one. So actually, Osaro, the way I got into the company is because I basically email the CEO and say that I'm very interested in learning more about the company, and then eventually I got this job. But I think if you're still a student, definitely use your time well when you're still in school. Talk to different people, grab organize coffee chats, and then understand different industry and trying to find out what you're more passionate about, and then after you're working, you can actually more specialize and focus on more specific areas, so you can really accumulate your know-how and experiences in for specific function. Because you don't want to be just like a generalist. You also want to be specialized in something where you can teach people or share with people.
Okay. And there's another question, it's a little similar. It's an audience curious about your experience in Amazon Alexa. And do you mind to share a little bit your 3 months experience in Amazon?
Oh, that was just an internship. That was the one I did over the summer. Okay. So that's why it's only 3 months. So I definitely like my experience at Amazon Alexa. But my experience is mostly in B2B, business-to-business industries, so I never intended to work on B2C industry. But the reason I joined them is because I want to learn more about Amazon Alexa at that time, because it's an upcoming area in terms of voice assistants, and also I want to learn more about best practice in product management in big companies like Amazon. And Amazon, I always like the company because I think it's one of the very few big companies that can actually continue to innovate. Most of the time when a company becomes more mature or becomes bigger, it's hard for them to come up with more innovative solutions. So I really want to know how Amazon is able to continue to be innovative even though they're such a massive organization. So the summer internships for me is more a learning experience I want to acquire, but before I even went to business school, my goal is always to work for smaller startups. So that's the reason.
Okay. We have about 5 minutes left, so maybe you can choose 1 to 2 questions to answer.
Okay, yeah, I think there's one answer, there's one question seems to be very interesting for me. It says that self-learning robot seems to move quite slow. What would be the solution to tackle this problem and strike the balance between precision and efficiency? I think this is a very good question. Because right now it's true, there's still a trade-off between precision and speed versus basically, I wouldn't call it efficiency, I would call it flexibility or dexterity. So the idea of deep learning is to allow the robot to learn through trial and error. So if you want to allow someone to make mistakes, you cannot expect him or her to be always accurate. So that's basically a trade-off between precision and dexterity. But this is just the current constraint. We believe that the technology will improve, and eventually deep learning or reinforcement learning can allow robots to be not just dexterous, but also precise. And I think that's going to take some time, and it's not something that can be achieved by just one company. But the reason that we think is very plausible in the near future is because there are now so many companies and so many research institutes and universities looking into this problem. So we believe that the trade-off between precision and dexterity will be solved pretty soon. And if you're interested in learning more about like similar examples in different industries, I think Clayton Christensen, a professor from Harvard Business School, has a very famous theory about disruptive innovation, and he talks about how lower-end innovations like personal computer, which seems to be having lower performance in the beginning, eventually catch up or even outperform mainstream solutions. And we think that might be the case. Right now, in robotic industries, most of the robotic manufacturers are very much focusing on coming up with more precise and more and faster robot arms. But they started to come to realization that artificial intelligence on the robot is also very important because that allows robot to handle a wide variety of different tasks, even though a robot may not be able to move that fast and that precise as they used to be. But it's harder for them to dedicate that much resources to actually work on artificial intelligence inside the company because their main customers are still mostly automotive manufacturers or electronic manufacturers. These customers, they don't need flexibility or dexterity. They need, because they're mostly mass production, so they need precision and they need the speed. So if they continue to focus on these mainstream customers, it's definitely hard for them to spend the equal resources on developing artificial intelligence. And that's why startups like us can come in and try to provide them with the solution. Is it almost time or should I pick another question?
We can take about 2 questions more, and you can view the question on Slido first, and I can ask the audience if anyone wants to ask in person. 现在有人想要直接现场发问的吗？就是目前还没有在 Slido 回答到，或者想要直接现场发问也可以。OK。
Hey Bastiane, this is Tracy. I'm an RD in California. My questions, I actually just posed my questions, and I work in the healthcare field. And I was just wondering, have you come across any AI working in healthcare which it can actually interact with patients, as far as you know? Thank you.
Yeah, I saw your question. Specifically about robotics, not really, because right now, as we just talked about, AI-enabled robotics is still slower and less precise compared to traditional robots. So, and under these circumstances, we definitely don't want this kind of robots to be interacting directly with patients, because in order to do surgery, definitely require more precise and more accurate solution than current technology. But I do know that there are quite a number of people looking into applying artificial intelligence in drug discovery, particularly to use basically large amount of data to help them to better or accelerate the drug discovery process. And I think even this area is still in a very early stage where people are still trying to figure out how to incorporate artificial intelligence in healthcare industry in general, because it's really hard to regulate. We already talked about that deep learning is essentially like a black box, and you don't know how to integrate it because the algorithm learns to adjust its parameters by itself. So in this case, if you can't even integrate it, how do you gonna file for FDA approval? And how do you regulate this kind of medicines? And if there's any issue with the drugs, who's gonna take responsibility? Is it the person who developed this algorithm, or is it the drug developer? So there's still lots of questions about applying artificial intelligence and drug discovery, but definitely like in the early discovery stage, some people still already started to look into that. But in terms of robotics in healthcare, I think it's gonna take a long time. As I showed you before, let me show you the previous slide. Basically, this slide, I think the technology will eventually improve in terms of accuracy, adaptability, and generality, but right now, because it's not precise enough and it's not fast enough, so you can't really apply the technology to other industries. So you can apply it to warehouse because it's fault tolerant. If you drop something on the ground, the worst case is just pick it up, as long as you don't damage the item. But if you damage an electronic part in a factory, that could be a significant cost. Not to mention that if you perform a surgery on the patient and if it's not accurate enough, it's not precise enough, that's definitely a huge cost and it's definitely mission critical. So I don't think that's gonna happen in the near future. I think the technology will gradually expand to different industries and will probably start with industries or use cases that doesn't require such a high precision and it's not so life critical.
Okay, then maybe we can have one question left. So Bastiane, you can choose one question to answer.
Okay. I saw one question about basically, is it possible to apply the self-driving car model, trend, and simulation to real world? So I will just answer this question. I think we talk. I think it was in my previous slide that we talk about the challenge in simulation. So simulation is definitely useful because it's just a lot easier to train model in simulation. But right now, it's still very, very difficult to simulate physics, not just contact, friction, but also gravity. We still don't see any one of the simulators that's able to simulate the reality perfectly. So it's basically not possible to directly transfer a model, trend, and simulation to reality. You definitely need to use other techniques, either just use simulation to basically prototype your model, and then use actual robot rollouts or actual real-world data to fine-tune the model, or you just need to train your model in real world. Because even if you apply domain randomization, so OpenAI recently published a paper about domain randomization where they train robot arm to be able to manipulate different objects between the fingers using just domain randomization. So they use zero real-world data, and the robot seemed to work. But still, they couldn't figure out why that happened. They tried to add more real-world data to train the model, which is trend and simulation, and that didn't improve the result. So it's a very confusing result, and still cannot be applied or commercialized in reality. So I think we still have a long way to go. Either we have to come up with better simulator, or we have to try to improve techniques like domain randomization or domain adaptation.
Okay, so thank you for answering all the questions and a great talk. And so let's give Bastiane an applause too. Okay, so the talk is over, and if you want to reach out to Bastiane, you can refer to her Gmail and Medium blog. 好，那这个 session 我们就在这边结束，然后待会是中午休息的时间，等下我先出来。